Welcome back. In this video, we continue our study of Chapter 3 about the applications of the mean value theorem. So we move to section 3.3, where we are going to clarify the relation between differentiability and partial differentiability. We know that if you have a function of several variables, then Frechet differentiability at a point implies the existence of partial derivatives at that point. But we gave an example showing that the converse is not true. However, if we put further assumptions, if we assume that the partial derivatives not only exist at a point, but they exist on the whole domain and they are continuous on the domain, then actually f is of class C1. Okay, so this is the main result of this section. So we have, as usual, a function of n variables defined on an open set of the product. So U is open, and so each EI is a norm space, and F is a norm space. So, so the result states that F is of class C1 on the whole domain U if and only if F has continuous partial derivatives on U. Okay. Now, one way is easy. If F is of class C1, then we know that the partial derivatives exist. And actually, the partial derivatives are the components of the Frechet derivative, of the total derivative, if you like. Okay. And this means actually that when I evaluate the Frechet derivative at A in the direction H, then this is actually an element in F. So this quantity this element is the sum, is a kind of dot product, if you like, between this vector and the vector whose components are HI, which is H. Now, each component is not necessarily a number. It is a linear bounded operator. Okay? So this linear bound operator acts on H1, the second one acts on H2, and so on. So this equation 1 implies that as a function of A, if f prime is continuous, then of course all the components are continuous. And conversely, if all the components are continuous in A, then f prime is continuous in A. And this is a standard result in topology. Okay. So continuity of a vector is equivalent to the continuity of all its components. So this is one direction. Okay. Now, conversely, suppose that the partial derivatives exists on U and are continuous. So of course, the partial derivative with respect to the ith component is a map from U into the space of linear bounded maps from EI to F. Okay? Because I have two variables here. When I apply this to A, I get a linear bounded operator, and then I apply it to a vector HI. So it's enough actually to prove that F is differentiable at every point A in U. Why? Because continuity follows from equation 1. Okay? If we prove that F prime exists, then it's necessarily of this form. Okay? And continuity of every component implies the continuity of the vector. Okay? So. And we have no choice. If the Frechet derivative exists, it must be of this form. Okay, so this is what we are going to do. So we pick a point, an arbitrary point A in U, and we'll show that the difference between F and this linear part is a small o of the increment x minus A. Okay, so here x is an element in U, which is a subset of a product space. So x is an n-tuple or a vector, if you like, and same thing for A. Okay. Now, of course, we can write this in a slightly different way. We can write it at f of a plus h minus f of a minus this equals small o of h. But I prefer this form because it's less confusing, as you shall see now. So this equation really means this condition. So for every epsilon positive, there exists a positive number eta such that the difference between f and its linear part is less than epsilon times this quantity, the distance between x and a, provided the distance is small enough, small than a number eta. And of course, you can put less or equal or strictly less. Strictly less doesn't really matter here. Okay. Now, as usual, we equip the space E, which is the product of EI, with the maximum norm. But this is not really important because we can also consider the one norm, the sum of all the components, or the Euclidean norm. Okay, all these norms are equivalent. So, and we saw that differentiability doesn't remains the same if we replace a norm by an equivalent norm. Okay, but I found this a little bit convenient. Okay, so a little bit more convenient than the sum norm. Okay, so pick a positive number epsilon, and now let us write the condition of continuity of each partial derivative at the point A that we fixed in the beginning. Okay, so continuity of the partial derivative, the ith partial derivative at A, means that if x is close enough to A, then the distance between their images is less than any positive number. So here I took epsilon over n and not epsilon. It's not really substantial, but if we want to get exactly epsilon here, we have to put epsilon over n here. But it's not really important. If we take instead of epsilon over n epsilon, then we will find n epsilon here. So it's not really important. Here, n is not a variable. N is the size, is the number of variables, so it's fixed. Okay? It's not a parameter that tends to infinity. Okay, so it's a constant in this context. Okay, but if you want to have exactly an epsilon here, we'll have to take epsilon over n. Okay, so this is the continuity condition. We have actually n continuity conditions, one condition for each partial derivative. Okay, so we'll refer to this condition as condition number 2, okay, because we shall use it. Okay, and now we rewrite this difference in this way. Okay, so the eta actually will be the minimum, the smallest between the numbers eta 1, eta 2, eta n. Okay, it will be clear why I chose this. Okay, so then since we assumed, of course, this condition that the ball of center A and radius eta I is contained in U is just a consequence of the openness of U. Okay. Because when I write the continuity condition, I must ensure that X is close enough to A and at the same time is in U in order for the partial derivative to be defined at X. Okay. But since U is open, this is not a big deal because I can ensure that X is in U and close enough to A at the same time. Okay, so the condition that so if eta is less or equal than all eta i's, then the ball of center A and radius eta is contained in the ball of center A and radius eta I for every I actually, and this is contained in U by construction. Okay, so now we are going to work locally near A, so more precisely in the ball of center A and radius eta, which is a ball in the product of EI. Okay. And now we fix a point x, an arbitrary point x in this ball. So the distance between x and A is less than eta, so it's less than eta I for every I. Okay, and now we write this difference between f and its linearization. We do a trick. We add and subtract similar terms. So x is x1, x2, xn, and A is a1, a2, a. Now we add and subtract this term, f of a1, x2, x3, xn. So we added and subtract. This term is the same here and here. So these two cancel. So it's just obtained by fixing the first component, first argument, by letting the first argument equal to a1 and the remaining argument x2, xn. And same thing, we add and subtract another term where the first two arguments are a1 and a2, and so on. Okay, so this term cancels with this term, this term, and so on. And the one before the last cancels with this one. Okay, so we are just left with f of x minus f of a. And this sum, we split it in a natural way. So this is a sum of, so here I wrote every term of this sum. Okay, the first term is partial derivative with respect to the first variable. Next term, second partial derivative, and so on. So this term plus this term plus this term is just equal to this sum. Okay. So what we are going to do is to prove that each term in the sum, or each line, if you like, is less than epsilon, or is, if you like, it's small o of xi minus ai. Okay. So the target is to prove that each line is small enough with respect to xi minus ai. And then I apply the triangle inequality. So the norm of this is less than the norm of the first line plus the norm of the second line plus etc. plus the norm of the last line. Okay. Now, so let us start with the first line. Okay, so I consider the first argument as a variable. So instead of x1, I put zeta1. For zeta1 sufficiently close to a1, and more precisely, since we are going to work locally, for any zeta1 whose distance to a1 is less than eta, we let g1 of zeta1 to be this formula. So just replace x1 by zeta1, second term is unchanged, and in the linear part, I replace zeta1, x1 by zeta1. Okay, so now we get a function of one variable defined on this ball, which is contained in this first space, capital E1. Okay. So why did I do this restriction? Because f is defined on an open set U. Okay, so I cannot put in the arguments of f anything I like, because the vector can be outside U if you don't put some restrictions. But if we choose zeta1, my choice of x and a, because x is sufficiently close to a, so this is not a problem. But I choose also zeta1 to be sufficiently close to a1, because in this case, as you may easily check, the argument of f, which is zeta1, x2, xn, belongs to the ball of center a and radius eta, as it's easy actually, because just evaluate the norm of zeta1, x2, xn minus a1, a2n. So I get the maximum of zeta1 minus a1 in norm, which is less than eta. Second is x2 minus a2, which is less than eta. So the maximum or the norm between zeta1, x2, xn and a1, a2, an, etc. is less than eta. And similarly for this argument of f. Okay, so this restriction of zeta1 tells me that these two vectors belong to the ball of center A and radius eta, which is contained in U, as we said. Okay, it's contained in the domain of U of f. Okay, so everything is well defined here. So this is the first observation. So we are really locally near A1 here, and we are going to apply the mean value theorem to this convex, to this ball. Second thing, if I put instead of zeta1 A1, I get these two terms are the same, would be the same, so they cancel, and here I get 0, A1 minus A1. So G1 of A1 is 0. And third thing, the reason why we introduced this function is that when I put instead of zeta1 x1, I get the first term or the first line in equation 3. Yeah, this is, remember, the first row of the equation. And now everything is constant here, actually. In my reasoning, a1, a2, an are fixed, and x1, x2, xn are fixed, but they are close together. The only variable is now here is zeta1. So when I differentiate with respect to zeta1, everything being held constant, I get the derivative of this term is just the partial derivative with respect to the first variable. This is a constant, doesn't depend on zeta1, and this term is actually linear in zeta1, linear and continuous, of course. So the derivative is just this linear bounded map, the partial derivative, evaluated at the point A. Okay, so our choice of zeta1, since I didn't write the proof, but you can, I told you how to check that. The n-tuple zeta1 x2 xn belongs to the ball of center A and radius eta, and I chose eta to be less than all eta I. So in particular, it's less than eta 1. So therefore, this n-tuple is at a distance of A at most eta 1, or strictly less than eta 1, actually. So I can apply the continuity condition too. Okay, and accordingly, I get that the distance between the partial derivatives is less than epsilon over n. Okay, this is why I chose eta less than all eta I, because I need all these conditions at the same time. So I took the minimum. Okay, and so I apply now the mean value theorem, version 3.3 to be precise, to this ball, which is a convex, an open convex set. And it follows that the distance between G1 x1 and G1 a1 is less than epsilon over n, which is an upper bound of the derivative, times the distance between x1 and a1. So the first line in equation 2, in equation 3 actually, is less than epsilon over n times the distance between x1 and a1. Okay. And similarly, for the next line, I set G2 of zeta2. For zeta2, of course, close enough to A2 in order for everything to be well defined. So G2 of zeta2 is the second line, but we replace x2 by zeta2. So this is well defined. When I put instead of zeta2 A2, I get again 0. And so the reason why we introduced this function is that it corresponds to the second. When I replace zeta2 by x2, I get precisely the second term or the second line in equation 3. Okay, and I can, of course, G2 is differentiable because f is differentiable. So the derivative of this guy is the partial derivative of f with respect to the second variable. This is a constant again, and this term is linear and continuous in zeta2, so its derivative is just this map. And again, my choice of zeta2 and of x, of course. This argument here belongs to the ball of center A and radius eta in the product space, of course. And my choice of eta, since eta is less or equal to eta 2, then this ball is contained in this ball. So I can use again the continuity condition 2 for I equal 2. And I get that the distance between the derivatives is less than epsilon over n. So I apply again the mean value theorem on the ball of center A2 and radius eta. So I get that the second line in norm is less than epsilon over n times the distance between x2 and a2, and we continue in this way until we arrive at the last line. So we set gn of zeta n to be the last line, but with xn replaced by zeta n, of course. So again, this is well defined. It vanishes at an, and the last line is gn of xn. Gn is differentiable, and we have this formula for the same formula. And our choice of the parameters imply that we can apply, sorry, there's an error here, equation 2. So the continuity condition 2 implies the same thing. So the last line, so the derivative of gn at zeta n is less than epsilon over n. Okay. So by the mean value theorem, the distance between gnxn and gnan is less than epsilon over n times the distance between xn and an. And now when I sum everything together, I get, so the first line in norm is less than epsilon over n times this plus etc. So, and now xi minus ai, because I chose the max norm, each norm here is less than norm of x minus a. So I can put norm of x minus a in common. So I get epsilon over n plus epsilon over n plus epsilon over n times x minus a. So I get, so this is at most epsilon times the norm of x minus a, and this is precisely the Frechet differentiability condition of f at a. Okay. So this concludes the proof and the video. So thank you for your attention and see you next time.